Hey, good morning or good afternoon, depending on where you're joining us from. But welcome to the webinar, everybody. Uh, we'll have the slides up in just a second. But just wanted to welcome you all to the webinar. We've done a webinar earlier this year, and we will be doing several more. So we're doing a series of webinars. Today, we wanted to, given all the kind of changes happening in the IT infrastructure space, around how you're building systems, how you're scaling them. We wanted to give a webinar where we'll cover some of the basic concepts and just kind of level set on the basics of messaging, and then we'll go into some specific examples around what makes NATS a bit different and a bit unique, and we have a demo, of course, as well. Let's go ahead and go to the next slide. So, hey, just a quick introduction. My name is Brian Flannery. I'm the community manager for NATS. You'll see at the bottom of the screen my contact information. As I said before, we're very interested in doing more webinars as well, so if you have any feedback, any ideas on what you might like to see in a future webinar, or any questions, just feel free to reach out. That being said, we will have a Q&A at the end of the webinar, so if you do have any questions as we're going, you should be able just to directly ask the question via the GoToMeeting, and the moderators will see your question. So just general housekeeping, any questions you have, go ahead and ask those, and we'll cover as many as we can at the end. And with that being said, I'm going to transition over to Alberto and let Alberto introduce himself and talk about some items he's prepared in his demo.
Great, thank you, Brian. My name is Alberto Ricart. I'm a principal engineer at Apsera. I have been building messaging-based systems and messaging-based applications for about 20 years. And with that said, I would like to actually start to show you and teach you how messaging systems work, review the different messaging patterns that we use for exchanging information, describe a sample application, and see how we can apply NATS and messaging paradigms to actually make our application much better. And with that said, some of the messaging basics. So there are four main elements to messaging. We have messages, which are the unit of data exchange. We have producers, which send messages to the server. We have consumers, which receive messages from the server. And we have the messaging server itself, which distributes messages from producers to consumers. Messages are basically just data that you send around, but they also have a subject that describes the message contents. The data that we shuttle around is application defined, so it can be anything that you want. Of important measure is a subject. The subject name is how we specify the destination of a message to the messaging server. It consists of one or more elements that are separated by dots. Each of these elements can be used, if you actually think creatively, to build message name hierarchies, right? So the individual message elements can actually be thought of something that could be useful for organizing the data that you move around. Also, right, depending on the service that you're doing, one of these elements could actually be of interest to a recipient. So for example, I don't know if you can see my cursor over here, if I have this subject name, PokéNATS even service 12.hb.123, some of these tokens may actually be important to the application. Producers send messages to the server, and whenever we publish a message, right, we don't really assume who the audience of the message is. What that means is that the producer is not really aware of who is subscribing to that message. We actually don't even know if there are any subscribers at all, right? And we usually try to be very general. We design messages to be general in nature and provide information that can be consumed by any number of subscribers, right? When a producer publishes a message, they have the option of actually specifying a reply, and if they do specify a reply subject on that message, that actually changes the semantic of the message from a notification to a request, and we will see how those work later. Consumers are the other side of the equation. They subscribe to receive messages that match a subscription. The subscription is based on the subject name that they have agreed to use. And optionally, they may specify a queue group name. And this is actually just an enhancement that enables multiple subscribers that are working together to solve a problem to be selected by the server so that only one of them actually receives the message. We will see how that works later in more detail as well. In addition to that, whenever we create a subscription, we can also specify how many messages we would like to receive before the subscription is auto-canceled by the server. And even though that sounds like a small thing, it's actually a very big deal. Let's talk a little bit more about subscriptions in general. Subscribers, when they specify the message that they want to subscribe to, can actually use wildcards. And wildcards enable the subscriber to match values in one or more of the tokens in the subject name, regardless of what the value is. So by using a wildcard, they can actually get many more messages that actually fit into that subject simply by doing a replacement. So anytime that a subject has a star, that particular element is replaced with any value that would take that position on the token. If we actually use the greater than symbol, the subject name could actually be as long as we want, and it would all match. Last but not least, the NATS server is actually the component that distributes messages between all the services that are actually talking through the message. Right? The NATS server is actually highly performant and extremely lightweight. It's about 10 megs in size. It's written in Go, and it supports a number of features that actually make it very resilient and powerful for deploying in cloud type scenarios. It supports cluster servers. That means that you can actually have many servers that are operating as one. So some of the clients will connect to one, other clients will connect to the other, and they can exchange messages through the servers without actually knowing who's connected where. If one server were to go down, for example, the clients would automatically transition to one of the other servers that is available in the cluster, distributing the load as necessary. Right. The NAT server, unlike many other messaging servers out there, actually uses a text-based protocol. And this is actually great because it actually enables you to use simple tools like Telnet to actually explore the protocol. In addition to that, right, if you start a server, you can actually specify a port where you can actually make HTTP requests and actually receive JSON information that describes the current health of the server and what it's doing. And this is actually very useful for building additional tools that work in supporting your application. One of the design features of the NAT server is that it protects itself at all costs. And what that means is that whenever there's a client that is actually very slow at consuming messages, right, the NAT server typically will actually kick them out. And then that way it prevents degrading the experience for other clients, right? Similarly, if a client actually sends a message that is actually a protocol error of some sort, the NAT server will actually disconnect. So it actually has a very simple behavior in how to deal with things that are not behaving in the way that we expect. The NAT server uses the delivery model of at most once. That means that you will get a message at most once. And in addition to that, we support many different client APIs and platforms. We have support for Go, Java, Node.js, Ruby, C, Microsoft.NET, Nginx, Python, Elixir, as well as a number of community contributed APIs for the server. If you happen to actually be using a language that is not supported in the list above, I actually am going to suggest that you actually become involved and actually develop and contribute that solution to the ecosystem. There's a wide range of applications that actually rely on streaming information actually coming in. The NATS server has a NATS streaming server counterpart that actually provides additional features that are built on top of NATS. And what a streaming server does is that it allows clients to actually publish messages to the streaming server, right? And the server will actually store these messages until some sort of limit is actually reached, right? Subscribers can subsequently actually come in and actually create subscriptions on those subjects and also specify where in the stream to actually get the messages. So the subscriber may actually come in and say, hey, give me the first message that you ever saw, or give me the last one, or anything in between, or something that is actually separated, let's say, 5 minutes ago. Right? So that's actually a very useful thing for certain types of applications. In addition to that, the NATS streaming server supports durable subscriptions, and what that means is that a subscriber may actually create a subscription, process a few messages, and then go away. At a later time, the same subscriber actually comes back in and actually can resume processing messages from that subscription right where it left off. The delivery model for the streaming is at least once delivered. So what that means is that you will get the message at least once if the server has it. You may get it multiple times. Now I'm actually going to do a little transition, and I am going to explain to you about how the different components communicate with each other and the patterns that we use for exchanging messages. There are three simple patterns that are used to communicate, and we have publish subscribe, we have queuing, and we have request reply. Publish subscribe is the basis of all the other communication patterns. A publisher publishes a message with a specific subject, gives it to the NATS server. The NATS server then distributes it to all the other consumers that have registered an interest in that subject, right? So this is a one-to-many operation. Based on that operation, there's another slightly different take on it, which is actually queuing. Queuing enables a NATS server to select a single consumer from members of a queue group to receive messages. So what that does is that even though the publisher is not aware of it, right, when he actually publishes the message, the server will select one of the subscribers to give the message that is sent. This enables the NATS server to then load balance the load for that particular message between multiple consumers. If a subscription that is made that doesn't use a queue group, that subscription will get a message the same way that it did before. So that guy would not be hampered. Mode of operation. Next we have request reply. And here we're actually going to start using that reply subject that I talked about a little bit earlier. And in this case, the publisher creates a subscription. This happens internally. Typically, the APIs handle this for you, right? But what the publisher does is he creates a subscription to a unique subject name that is only going to be used for the particular interaction that is going to occur, right? He also sets the maximum number of messages that he's interested in receiving. And then he publishes a message, given the reply subject that he selected and made the subscription on. All the subscribers that have subscribed to receive that message will get that message and publish a response. But the server, seeing that the client was only interested in getting one or two messages, right, will auto-terminate that subscription at the server level right when that qualifier is met. So what this does is actually make for very efficient one-to-one request reply where you have a really large number of consumers. And when we say really large, we're really talking Google scale, thousands of services responding, to that request. There's another way that request reply can operate, and this is very similar to before, but it combines the queuing operation that we saw earlier. And what happens here is a group of subscribers will actually form a queue, right? They will use a queue group name, make a subscription on a subject, and then the publisher making the request will actually publish a message. The server here, instead of actually delivering the request to all the clients, it'll auto-select one from that queue group and then give the request to them, right? That guy would actually respond to the reply subject that the producer provided, and then the response makes it back to the publisher. With these very simple messaging patterns, we can actually build massively scaled services that achieve many features which would be very hard and require a lot of effort to do otherwise. So we can address a very large number of clients, we can support discovery, we can create services that watch other services, and respond to the general health of our applications. We can do load balancing. We can do fault tolerance. And because messaging is location transparent, we're not really aware of who is actually making a request or who's providing the response. We can actually scale in different ways. So microservices and messaging is actually a really good combination because we can actually use messaging for inter-service communication using the 3 patterns that I showed earlier. And then if we build additional functionality into those clients, we can start building a whole platform that can actually be managed by the same messaging infrastructure. So for example, the services may actually start broadcasting heartbeats that provide health information. A control plane service could actually be listening for those heartbeats and then dynamically decide whether to grow or shrink the different services that we have based on the health of our application, right? In addition to that, we can actually use messaging to adapt the information that we are receiving from some publishers and some subscribers to some format that other publishers and subscribers can actually consume. And what the benefit of this is that, for example, if we had 5 services and we needed the 5 services to talk to each other, usually that would involve creating a number of around 20 integrations. If we use an adapter pattern where for each type of data that we want to adapt, we create one guy that can actually adapt them, really all we have to do is 5. And that's a lot less work than doing it the other way around, so we like that. So now I'm actually going to take a little bit of a site tour. And I actually want to take a case study and actually see an existing application that many of you may be familiar with, and try to see how we could actually make a similar type of application and then incorporate some of the things that we have seen related to messaging and enable this service application to be highly scalable. Okay, so what can we do? So let's say that we want to design a very small service-oriented application. We're not going to count that we're going to have millions of users, but we're going to keep that in the back of our minds just in case it does happen. We will release this application as a minimum viable product, right? So many of the features, even though the application may have some functionality that is useful, are not going to be complete. And as the product matures, we will add more and more features. So how would we develop this? We could simply make the services the way that we're used to, which is actually use HTTP and REST to actually communicate between them, right? But then very quickly, if we start keeping in mind that we would like to scale to millions of users, would that actually scale? And yes, it could, but it would require quite a bit of effort, right? And the next question would be, what would we have to do to actually manage such application, right? If we have to scale it, what are the paradigms that we actually have to implement? What systems do we have to introduce in order to do that? And as we mature our application and we develop it, and we introduce new features and introduce fixes to existing features, how do these changes and their deployment affect the running application? Let's take something that is very simple. Let's take a look at an application that actually came out this summer called Pokemon Go. And this is a phone application that has taken the world by storm. It's a augmented reality game that basically motivates people to actually walk around. So you pull your phone out, it gives you a map, it shows you where you are, and then it shows you areas where there are these things called Pokestops. And what you do is you actually walk to the nearest Pokestop, use your phone to interact with the Pokestop. The game then gives you some sort of game assets, right? These Pokeballs that you will use to actually capture Pokemons. Along the way, you may actually find Pokemons. You can actually tame them, and then as you progress in the game, you may be able to actually level and evolve these pets to make them more powerful. Ultimately, at some point, you may be able to actually use your pets to actually battle other players. So that actually is an interesting example, but really, what is all of that and what does it mean? Well, at its core, the Pokemon Go application is a massive sensor collector. It operates in a very large-scale playground because it's actually using geographic data. The users are out in the real world, right? And every few seconds, they're actually contributing new location information to one or more servers. Every once in a while, the game will actually produce some assets, some Pokemon, and the user then can interact with that. So just taking a little look back at that, we start realizing that for each million of users that we have in our game, we're really incurring 12 million interactions just to provide the sensor information. That doesn't include returning other things and notifications of now we have a Pokemon that is nearby or not, right? So that's actually great, but it starts pointing out that the scale starts building up very quickly, and sometimes becoming successful will create a nightmare. So now imagine that your application becomes very popular and you get 130 million adopters. That's actually nothing to sneeze at. And in a little time, right, this little application that does very little things in cloud scale becomes a huge thing. Any application that has 1,000th of the success of this one is already a non-trivial application, right? There's issues related to authentication, data persistence, and business logic that we have to deal at this scale, monitoring and management, etc. So with that in mind, now I want to think about how we would take an application like that, use microservices and messaging and NATS to implement it in a way that we can actually maybe cope with that level of success. So here's the PokéNATS architecture. We have a REST proxy, and web browsers actually come in and they make requests into a REST proxy. When the REST proxy gets a request, it creates a representation of the player that it's called a trainer, right? The trainer is a messaging-enabled service that represents a player, and it enters the world. When it enters the world, it actually goes to a service that provides some sort of data backend, right? Retrieving some sort of persistent information. Think in terms of login and cookies, right? The trainer will actually emit updates to other trainers. So them being in the world actually contributes to the game experience. And as the trainers are actually in the world, they receive these updates from other trainers. They're not really interested in all the possible trainers, because if we were listening for 130 million updates from other players, our phone, first of all, would die, and that would be a very bad thing. So they only really care about trainers that are nearby geographically, right? So they limit the number of updates that they get to only those that are near them, right? And reduce noise that way. When the trainer has received enough updates from other players, that trainer emits a spawn request. So he sends a request to the agent service to actually create a spawn. In response, the agent service publishes a new message that actually implies that a PokéNAT is actually coming into the world. And a PokéNAT is just simply one of the letters of our logo appearing on the map. Right? That's really all the application is. It will also have some other attributes that make it interesting in terms of the game, which will be, it'll give it a location somewhere on the map. There's going to be near the trainer that spawned it, and it'll have a size, so it'll have a level. It'll be bigger or smaller, and of course it'll be either an N, an A, or a T, or an S. So, in addition to that, we also have other microservices that are running in here. For example, we have an invalid message service, and this guy is simply subscribing to PokéNATS monitor log invalid. And these messages are messages that are going to be originated by any of the other services that are actually running in the system. And if these services actually get a request or receive a message that they didn't expect, or wasn't formatted, or didn't have valid data, right? They would actually grab that data that they received and send out a message, including that data, to the invalid message service. That way, the invalid message service could eventually grow into something like detecting whether there's some denial of service attack going on, or whether there's some sort of other problem that needs correction. The control service over here is actually a control plane type service. So what this guy does is it says, that the required services for our application are the data, Eden, and invalid message service. And he effectively is subscribing to heartbeats that are actually generated by these three services. And if he deems that one of them is not available, he will actually spawn a new instance of those services so that they actually fit the gap that is missing. And without doing too many graphically, what that means is, and I'm going to require a little bit of time to actually come over here. I'm going to basically sign in into my little PokéNAT application, and then I will see that I basically just downloaded a Google map that is actually taking my location from what the browser is providing, and then it puts me into the world. As the game time actually progresses through, we will see that the PokéNATs will actually start spawning. So we actually have to wait a little bit, and what we'll do is we'll come back in a few seconds. And I think that I actually saw one coming in. Oh, there they come. Here they come. So the PokéNATs are actually spawning, and we see them going in. As I said before, we require more than one player in order to be able to actually make the PokéNATs come. So in hopes of actually extinguishing some of the magic, yes, I do have a couple other players near me. I created them myself, and there they are. So, let me continue. So now, going back here, how do we deal with this? So another thing that I actually paid a lot of careful attention to is actually the subject names that we use to communicate between the services. Again, remember that each of the elements could actually have some sort of meaning. And in terms of this application, what we did is we have a root name, that the game itself actually uses that is called PokéNATS. And then we follow that by a service type. And the service type is going to be something like trainer or data service or Eden service or control service, right? And the ID is going to be a unique instance that actually designates what that process is. So all of them actually have their own ID. And whenever they publish some sort of information, they include that information in the message that they're publishing. In addition to that, they actually provide some geographic, geolocated information that is actually used to filter information that is moving through the application. So for example, the player, as he's walking through the world, will actually say, hey, I put something on grid 5. And only guys that are actually near grid 5 will actually receive it. The subscription is actually keying off of that to eliminate a lot of the work that happens, right? The game events, or the event that I have over here, are the different types of things that could happen in the game. So for example, the trainers are actually submitting updates all the time. The initial login that the trainer made to the data service was actually a data request. The trainer then actually requested a new spawn from the Eden service, and the Eden service responded by publishing a spawn event, right? The administrative type commands that are used by the control service, for example, have a different root. They are actually called PokéNATS_admin, and they have different commands that actually force the individual services to do different things. So there's a discover command that, when sent without any qualifier following, for the service type and ID, as I explained up here, actually affect all services that are running over there. So somebody could actually come in and actually request to find out all the things that are running in my application. Or they may supply, for example, the service type and eliminate anything that doesn't match the data service. So that all the data services will actually be able to answer that and say, I am here, right? Similarly, the admin command supports other verbs like kill, right? So let's say that we actually want to terminate one of these services because we're starting one elsewhere. You could actually send a message to one of these services and target him to actually go away, right? In a similar vein, we could also send a configuration update. So we could actually say, hey, you know what? The server is actually experiencing a fairly large load with the trainers right now, and the number of heartbeats is too much for the service to actually cope with. So let's actually change the rate at which we publish the update events by sending a configuration setting. So that's something that could be done. and then that way achieve some utility with that. In addition to that, all services actually publish their service type ID and hardcode. And that's actually what enables the control service to actually know if the data, the EDEN, or the invalid message service are actually running, right? So that information can actually be used for some purpose. They could also include other things like what is the memory or CPU pressure on the system where this is actually running. And then you can actually start seeing possible solutions that you could implement to make your application more responsive to the current environment settings. Logging. So we don't want to do anything silent. We want to know what our services are doing. So instead of actually logging into some file that we maybe have to look at or some server where we have to look, the servers are actually logging to the network. So they simply create a message and they provide either an info or an error type moniker attached to the end of the subject, right? So they provide that to the element of the last element of the subject, and then basically just publish it. So then that allows a simple tool to actually receive error logs and maybe archive them. Or maybe I actually want to debug my system. I could actually subscribe to see what kind of error messages a particular instance of my service is actually generating. This is that kind of flexibility that careful choosing of what my subject names are enables me to do. So by now, I think we should have quite a bit of Pokemons here. And yes, we're seeing that there's some Pokemons actually coming over there. I'm going to actually refresh them. And we see that they're actually coming along and growing there. So we go back. So scalability. How do we achieve scalability in our application? Well, we made all of our services be able to use a queue group name. This enables the subscriptions to be load balanced by the NATS server itself. We created also subject names that we can filter on, and that enables to filter the work that individual services have to do, maybe only dealing with specific localities to do their work, right? The trainers actually do this. Some of the services could actually do that, right? And then also, we also have the possibility of saying that if we have a request reply type of service and we know that there's all these ones, whenever we publish a request, the particular service could actually look at its current load in memory and CPU pressure, right? And decide, you know what, I'm going to respond, but I'm going to delay that response for a few milliseconds. And if I don't respond, I will allow somebody that maybe has more capacity than I do. So that's one way that we can actually, start scaling how our services are dealing with, the current loads on the system. So in terms of service discovery, we actually made all of our services be able to understand that a message could be sent to them and for them to announce themselves as being there, right? This enables other services like the control plane to basically understand that there's maybe missing services. And if there are services that are missing, maybe we need to start them. The control service can actually do that, right? We can actually limit the impact of the request based on a specific subject name. So we can use the subject name again to actually say, my control service is only going to deal with things that are on a particular grid. And maybe he's only responsible for a particular geographical area, right? So we can combine these things, right? Fault tolerance. We can have as many instances of our services as we need. If one of them actually goes down, it doesn't matter. The load will be taken over by the existing ones. If a new one gets added, the service will auto-heal and it'll grow. If we configured our service to be in cluster mode, right, whenever the clients actually connect to NATS, they will randomly select one of the servers that are part of the cluster. We distribute the load between different servers. If a server disconnects or goes away, the clients automatically select a different server to connect to, and they connect, right? So we didn't have to do anything. That just happened, right? In addition to that, right, we can react to whatever's going on. We can prune, we can add, we can do whatever we need to do in order to make sure that our application continues to run, maybe in different qualities of service, but running nonetheless. Load balancing. Again, the queue group functionality that we have on subscribers can actually help here. in terms of the proxy, we're actually using HTTP REST endpoints. For that, we would actually have to use HTTP redirectors. These are servers that are simply listening for the initial HTTP request, and then based on some other information that they have, right, they create a redirect, right? So they actually redirect the browser to actually go to a different server and actually pick up the load in a different place. That's one way we can deal with that there. For monitoring, we enabled all the log messages to actually work over the network. Every time that one of our services logs something, it does so to the network in addition to its console. So we can actually create tools that view them over the network, even the simple, and I actually want to show you how that actually works over here. So we can actually go over here, and I have, let me minimize this a little bit. I can come over here, and for example, just by using a regular simple subscriber, I can actually listen for things that are actually happening on my world, right? So I can see that, you know, the Eden service is actually publishing things. I can see, I can subscribe to the different heartbeats that are actually coming through. All of this is actually live. You know, how my tools interpret that is something that I decide. But even without writing any code, just using the sample programs that are actually shipped with the NATS server, we can actually do this. So if I actually want to see all the logs that are actually being generated, all I got to do is subscribe to that subject. And all of a sudden, you know, the logs actually start happening. I didn't have to do anything. I see it all happen. Awesome. You know, and also, I want to show you one more thing. So I didn't make any assumption of the type of messages that different tools will receive. So for example, I created a small tool that simply says, I'm going to give you the number of clients that I know have been around in the last 3 minutes. And every time a new client actually comes in, I will actually update that. So if I actually go ahead and maybe do a new window here, and I'm actually going to copy that URL that I have over here. I'm going to paste it. And I go to the live application over there, and I'm going to say foo@test.com, right? I will see that that number will actually increment in a few seconds. As soon as this client is actually able to see a heartbeat, he will actually update. I'm still logging in, he hasn't picked it up, but he will. And we can come back, we can actually start seeing the client right there. There we go, my client updated. Right, so we see that guy actually coming in. I also wrote another tool that actually keeps track of the rate of the different NATS letters actually spawning. So I can see that the N has spawned 1,456 times, the A has spawned 1,549 times, they just updated the T, and so forth. Right? So I can make general purpose tools just by tapping into the information that is actually flowing on the messaging server. So management, right? By providing and building control functionality into my clients, I can do things like update configuration settings. I can kill them. I can make them make themselves known. Right? That becomes useful as I write tools. So now another area, right? So now I have been working on my application for a while, and I know that messaging is actually making it better for me to do my services. What does it mean to add a new version of the service? Well, for one thing, because my producers and subscribers are not tied to each other, right? Whenever I add a new kind of service, I don't really affect the existing ones, right? Unless they're actually, sharing on the same subject and doing different things that maybe throws my other clients out of whack. There's no kind of effect that I can do. So I can pull the existing information that I'm seeing, generate new information, and put it back on the network, right? This also has a side effect that I can do other kinds of things, right? So as I develop my different services, I may have a new version that I want to deploy, and after I kind of pretty sure that it works correctly, what I can do is actually run it on the production system. So I don't have to stop the existing one. All I have to do is start one instance of the new service. And if I see that that service is actually behaving properly, right, I may start to add more. And as I see that clients are actually connecting to it and actually working with it, and I become reassured that my service is working properly, I can actually start stopping the old versions of the same service. So I can then transition, to my new implementation, right? If on the other hand, I actually detect that my new version actually did something bad, and I'm actually breaking the system, all I got to do is actually send it a control command and I kill it. I'm done, right? I didn't affect anything. I probably affected one or two clients or a few clients, but I didn't affect the entire application. I only affected a few things, and depending on the number of services that I have, the number of clients that I affected are probably very limited, right? So that's actually a great feature. So let's say that then I add a new system, and that new system then also takes a new data format that I have not used yet inside of my services. Well, if I actually message enable it and I adapt it, I can make that data that system holds available to my other services that I have running. And I didn't have to do anything. All I had to do is one single integration point. They're all talking messaging through NATS. And I can now access that system. I could write data to it. I could make that system do something, or I could read data from it. Okay? That's an awesome thing. So the takeaway is, by using message-driven microservices, I can make them much better. I can make them much smaller. And I can make them highly scalable and more manageable. I can cope with change. I can cope with my innovation. Right? I made my code simpler because things behave in a predictable way. I made it more robust because I can run multiple instances of these things. So if one gets taken out or one set of servers gets taken out, the load will transition elsewhere. These are all great things. Thank you.
Excellent. Thanks a lot, Alberto. And we're going to go through some Q&A now. So I saw quite a few questions coming in. And let me just pull them up, and we'll start to go through some of the Q&A. So Alberto, it looks like the first question we got was someone was asking if they're already running NATS server, what would they need to do to get started with NATS streaming?
So NATS streaming is a little bit different than NATS. It is actually based on NATS, and it uses NATS. But the streaming server has its own API. It's very similar to what NATS is, right? But realize that what you're doing when you're using the streaming API is you're actually publishing and consuming from the server, right? So clients, right, publishers, will actually publish information to the streaming server. So really what you have to do to get going with it is you download the NATS streaming server, and you also get the NATS streaming API, and that's it. You're ready to go. You don't even need to actually have a NATS installation to actually use it, which is actually a great thing.
Thanks, Alberto. The next question was someone was asking if they're running a fairly lightweight device, like something that's using an Arduino or library or maybe a Raspberry Pi. Is that something NATS would be a good fit for?
For sure. As far as I know, actually, we've already done that. I believe that we have Arduino and Raspberry Pis that have had NATS actually installed and running on them, right? That's the idea. The NATS server is actually very, very, very small. It's about size, right, or a little less, and it just runs, right? So you can build it for the platform, you can deploy it on the device, and now you have a messaging server right there, right? And realize that there's actually two ways that you can actually do it. You can just do the client, right, and have the device talk to the other server. So you can slice it and dice it however you think you might want to do that.
Okay, and let's see, the next question we had was someone was asking, since NATS is a plain text protocol, that's great that it's simple, but they were wondering about how secure it is.
Actually, it's very secure. NATS supports TLS, so that means that you get behavior where the clients can actually authenticate themselves to the server, and they can also use the TLS information to encrypt the communication between the server and the client, right? In addition to that, we also support access control groups. So what that means is that we can actually say that a particular subject, like the admin subjects that you saw, that I was actually doing for the service administration, can only be published by people that you know, right? So even though they're floating around in the system, only specific clients with a particular ID are able to actually publish them. Similarly, you can actually limit who can subscribe to them. So then that way you can actually provide security to it. And the other thing is, the NATS message payload is actually binary, right? So if that wasn't sufficient or you wanted to do something else, it's still possible for you to actually encrypt the payload that you put inside of the message. So you could handle that yourself if you wanted to as well.
Excellent. Thanks, Alberto. I see a whole bunch of questions. I'm going to take a couple more. But what we will do, if for anyone who did ask a question that we don't get to, we can definitely follow up in the Slack channel, or I can reach out via email as well. So I see quite a few questions. I did see someone asking if NATS messaging is for server-side only, or does it apply to client apps like, for example, browser and mobile also?
Oh, it could apply for all of them, right? I mean, obviously you can just have, anywhere where you could use messaging, it's a good thing for it, right? The application that I have, you could actually run on mobile, right? I mean, we have a Java API that you can actually do on Android, right? I believe that there's actually an iOS client as well, right? That exists over there that the community made. So you can actually embed these things and make your applications use messaging and use NATS. So yeah, for sure.
Excellent. And just one more question. Someone was asking about clustering, if NATS server allows you to cluster across VPN connections.
Yes, you can actually cluster the services. The server supports one hop full mesh clustering. That means that the server will actually forward messages to one of its neighbors, only one hop away, right? But it knows about all of its members of the cluster, right? So it supports that. That's one of the big features that we have.
Okay, excellent. Thanks. So as I said, everybody, thanks for joining. What we will be doing is we will share the slides as well as recording the webinar when that's ready. So this will all be available after the webinar. And then, as I said, we have quite a few questions. What we'll do is I'll follow up with those who did ask questions. We'll get your questions answered. Or if you join the Slack community, you could find that right on the NATS website. If you just go to nats.io/community. That's a great place as well if you want to follow up some questions. But I want to thank everyone for their time. Thanks for coming. And we will talk to you soon and follow up with you on that.
Thank you.